We now move from univariate extremes to multivariate extremes, where the central issue is no longer only how large an event is, but how several extremes occur together. This section explains why extremes must often be studied in several dimensions. First, many catastrophes are naturally multidimensional. A storm may combine wind and storm surge, floods may combine rainfall and soil saturation, and financial crises may involve correlated defaults. Second, tail dependence is crucial for joint risk in a portfolio or in a spatial risk map. The key question is not only whether one component is extreme, but whether several components become extreme together. Third, classical correlation can be misleading in the tail because it describes average co-movement, not necessarily joint extreme behavior. The goal is therefore to extend univariate extreme statistics to multivariate objects, such as componentwise maxima, and to derive limits that preserve the geometry of joint tails. Here the observations are random vectors rather than real valued observations. The first object is the componentwise maximum vector. For each coordinate, we take the largest value observed in the sample. This is the natural extension of maxima to several dimensions. The second object is based on upper order statistics in a radial sense. We first choose a risk functional, such as a norm, a sum, or a maximum, and then we study the observations with the largest risk scores, together with their directions. The third object is the exceedance count of a tail region, where the region defines what we call a large multivariate event. Finally, high exceedances can be defined through conditional laws, either component-wise, radially, or through a general rare set. This slide emphasizes that in several dimensions, there is no unique definition of being extreme. The first notion is component-wise. All coordinates exceed their thresholds. This is very restrictive and corresponds to simultaneous extremes. The second notion is that at least one component is large. This captures union of tails events, which are often relevant for losses triggered by any extreme component. The third notion is radial or region-based. An observation is extreme when a chosen risk functional is large or when it belongs to a specific tail region. The figure on the right illustrates these competing definitions in 2 dimensions. The thresholds define a rectangle, the gray region corresponds to a generic extreme set, and the plotted points show how different definitions select different observations as extreme. This slide introduces a fundamental distinction in multivariate extremes. In the bivariate case, the tail dependence coefficient measures the limiting probability that one component is extreme given that the other one is extreme. If this coefficient is positive, we have asymptotic extremal dependence. Joint extremes remain visible in the limit. If it is 0, we have asymptotic extremal independence. Joint extremes become increasingly rare compared with marginal extremes. The modeling consequence is important. Max stable and multivariate generalized Pareto limits naturally represent asymptotic dependence. When the data are asymptotically independent, one generally needs extensions. For example, mutual or higher order forms of asymptotic independence. We now focus on multivariate max stable distributions, the natural limit laws for component-wise maxima after marginal normalization. This slide extends the max domain of attraction to random vectors. We start from the component-wise maximum vector, which records the largest observed value in each coordinate. As in the univariate case, a non-degenerate limit requires centering and scaling. But now these operations are applied component by component. The definition says that the joint distribution belongs to the max domain of attraction of a limiting distribution if the normalized component-wise maxima converge in distribution. The important point is that the limit is not just a collection of marginal extreme value distributions. It also contains the limiting dependence structure between the extreme components. Here we define multivariate max stability. A distribution is max stable if the maximum of several independent copies has the same distributional form after suitable affine changes of scale and location. The key fact is exactly parallel to the univariate case. If a multivariate distribution is in a max domain of attraction, then its limiting distribution must be max stable. This result explains why max stable laws are central in multivariate extreme value theory. They are not chosen for convenience only. They are forced by the limiting behavior of component-wise maxima. This slide separates the role of margins from the role of dependence. Each marginal distribution of a multivariate max stable law is a univariate generalized extreme value distribution. We can therefore standardize all margins to a common form, usually unit Frechet. After this transformation, the marginal tail behavior has been removed from the problem. What remains is the simple max stable distribution, which contains all the extremal dependence. This is a very useful strategy. First standardize the margins, then model the dependent structure on a common scale. This slide announces 5 complementary ways to describe the dependent structure of a simple max stable distribution. The first is through the exponent function and the exponent measure, which give a complete analytical description. The second is Pekan's representation, based on a spectral measure. The third is the stable tail dependence function, which is often useful for statistics. The fourth uses d-norms, giving a norm-based characterization. The fifth is the spectral representation, which interprets extremes as random storms with random magnitudes. These approaches are mathematically equivalent in spirit, but each gives a different insight into extremal dependence. We first consider a simple max stable vector with unit Frechet margins. The joint distribution can be written through an exponent function displayed on the slide. This exponent function gives a complete description of the dependent structure. Its key property is homogeneity. If all components are multiplied by the same factor, the exponent function changes in a simple inverse way. The normalization conditions ensure that the margins remain unit Frechet. The message is that once the margins are standardized, modeling a multivariate max stable distribution is essentially equivalent to modeling a homogeneous exponent function satisfying appropriate marginal constraints. The extremal coefficient provides a quick summary of dependence. It measures the effective number of independent extreme components. A value close to 1 corresponds to complete dependence, while a value close to the dimension corresponds to independence. This is only a summary, but it is very useful for interpretation. The second part of the slide introduces the exponent measure. Instead of describing the joint distribution through the exponent function, we describe the mass of extreme sets. The exponent measure is homogeneous, meaning that tail regions rescale in a precise way. This measure-based viewpoint is particularly useful for connecting multivariate extremes with point processes. This slide introduces the radial angular decomposition of the exponent measure. The idea is to split an extreme vector into 2 parts. The radius measures the overall size of the event, while the angle describes the relative contribution of each coordinate. The exponent measure then decomposes into a universal radial part and a finite angular measure, often called the spectral measure. The radial part captures the fact that we are in the tail, while the spectral measure captures how extremes are distributed across components. This separation is central. It tells us that extremal magnitude and extremal direction can be studied through 2 distinct objects. The figure gives a geometric view of the previous slide. Points far from the origin correspond to extreme events. The diagonal dotted lines represent levels of a radial norm, and the cone-shaped region represents a set of directions. In this representation, an extreme observation is decomposed into a distance from the origin and a direction on the positive sphere. The angular sector, marked in the figure, collects events with similar relative component sizes. This is why the spectral measure is so important. It tells us where extremes are located directionally. For example, whether they tend to concentrate near one axis or along balanced directions. Pekan's characterization gives another geometric description of the dependent structure. It uses the unit simplex, where all coordinates are non-negative and sum to 1. On this simplex, the spectral measure describes the angular distribution of extremes. The displayed expression shows that the exponent function can be recovered by integrating the largest weighted contribution across the simplex. The normalization conditions guarantee that the standardized margins are correct. The main idea is simple. After marginal standardization, the whole extremal dependent structure can be encoded by a finite measure on the simplex. This slide explains how to read the spectral measure geometrically. If the mass is concentrated near the vertices of the simplex, then extremes tend to occur in one component at a time. This corresponds to weak extremal dependence. If the mass is concentrated near the center, then extremes tend to be balanced across components. which corresponds to strong extremal dependence. Independence corresponds to mass on the vertices, while complete dependence corresponds to mass at the center. The takeaway is that the spectral measure provides a concrete and visual parameterization of simple max-stable laws in several dimensions. The stable tail dependence function is another central object for multivariate extremes. It is defined as a limiting probability of at least one marginal variable entering a very high tail region after marginal standardization. In words, it measures the asymptotic size of a union of marginal tail events. The second part of the slide explains its link with the simple max-stable distribution. Once the margins are standardized, the stable tail dependence function and the exponent function contain the same information. This makes it particularly useful in statistical modeling because it directly targets the joint tail of the distribution. The d-norm characterization gives a norm-based way to describe multivariate max-stable distributions. We start with a non-negative random generator whose components have mean 1. From this generator, we build a norm by taking the expected maximum of weighted component sizes. The theorem states that a distribution is simple max-stable if and only if it can be expressed through such a d-norm. In particular, the stable tail dependence function is exactly this norm. This representation is useful because it turns the dependence modeling problem into the construction of an appropriate random generator. This slide gives a constructive representation of simple max-stable vectors. The idea is that extremes arise as the maximum of many random events, or storms. Each storm has a random magnitude and a random shape. The random magnitude comes from a Poisson process, while the random shape is described by the spectral random vector. Component by component, the observed extreme is obtained by taking the largest contribution over all storms. This representation is very intuitive for spatial or environmental extremes where a single event may generate a whole pattern of large values over several locations. This slide connects the spectral representation to the finite dimensional distribution. The exponent function can be computed from the spectral random vector by looking at the largest normalized contribution among the coordinates. When all thresholds are set equal, the joint distribution is summarized by the extremal coefficient. This coefficient is the expected maximum of the spectral components. Again, it ranges from complete dependence to independence. The important message is that the spectral representation is not only a simulation device. It also gives an explicit way to compute the joint distribution and simple dependence summaries. We now turn to multivariate threshold exceedances. The goal is to extend the peaks over threshold approach from univariate GPDs to multivariate GPs. In one dimension, exceeding a threshold is unambiguous. In several dimensions, however, there are different notions of excess over a threshold vector. The first is the L-type event. At least one component exceeds its threshold. This is natural for union of tails events and for many loss problems. The second is the R-type event. All components exceed their thresholds. This is more restrictive and captures simultaneous exceedances. The slide also mentions events defined through a loss functional, such as the maximum or minimum of the vector. The practical message is that the choice of exceedance region must match the risk question. The figure illustrates the distinction between the two types of threshold exceedances. On the left, the shaded L-shaped region corresponds to the event where at least one component is large. This region includes points that are extreme in the first coordinate, in the second coordinate, or in both. On the right, the shaded upper right region corresponds to the R-type event, where both coordinates exceed their thresholds simultaneously. The dot marks an observation close to the threshold boundary. This visual comparison makes clear why the L region is broader and more suitable for general multivariate peaks over threshold modeling. This slide presents the multivariate peaks over threshold approximation for L-shaped exceedances. The probability of a failure set inside the tail region is decomposed into two factors. The first factor is the probability of entering the tail region. The second factor is the conditional distribution of the excess given that the vector is in the tail. The modeling idea is to approximate this conditional excess distribution by a multivariate generalized Pareto distribution. This is the multivariate analog of the univariate peaks over threshold method. Model exceedances above a high threshold using a universal tail family. This slide defines the standard multivariate generalized Pareto distribution. The key representation is a decomposition into two components. The first is a common exponential shock, which measures the overall severity of the extreme event. The second is a non-positive deviation vector, independent of the shock, which describes how far each component is from the maximum. In other words, the common shock sets the level of extremeness, while the deviation vector describes the multivariate shape of the event. This representation is important because it separates severity from dependence, and it gives a constructive way to interpret multivariate threshold extremes. The general multivariate GP distribution is obtained from the standard version by applying marginal generalized Pareto transformations. Each coordinate receives its own scale and shape parameters. This allows the model to capture different marginal tail behaviors across variables. The slide also states that, conditional on a component being positive, each marginal distribution is a univariate GP. This is the direct link with the classical peaks over threshold theory. Thus, the multivariate GP combines univariate GP margins with a dependence object that controls the joint structure of threshold exceedances. This slide provides an illustrative model leading to a multivariate GP limit. The random vector is built from a common exponential shock plus a noise vector. The common shock creates simultaneous tail behavior, while the noise vector introduces heterogeneity across components. The proposition states that, conditionally on a high L-type exceedance, the excess vector converges to a standard multivariate GP distribution. The dependence object in the limit is obtained from a tilted version of the noise distribution. The takeaway is that a simple common shock mechanism naturally produces multivariate peaks over threshold limits. Threshold stability is a consistency property. If a multivariate GP model describes excesses above a high threshold, then it should still describe excesses above an even higher threshold after updating the dependence object. In the standard case, the slide states that conditioning on a higher L-type threshold preserves the multivariate GP family. Only the deviation component is updated. A special simplification occurs when all threshold components are shifted by the same amount. In that case, the deviation distribution remains unchanged. This mirrors the univariate idea that raising the threshold should not take us outside the same tail family. This slide extends threshold stability to the general multivariate GP case with arbitrary scales and shape parameters. When the threshold is raised, the scale vector is updated, while the shape vector stays the same. The dependence component is also updated through the corresponding standard scale threshold. This is the exact multivariate analog of the univariate GP threshold stability property. The key message is that the shape parameters remain invariant under threshold increases, while scale and dependence must be updated consistently. This slide points out an important caveat. In dimensions greater than 1, taking a subvector of a multivariate GP vector does not automatically give another multivariate GP distribution on its own support. To recover an MGP structure, one must condition on the event that at least one component of the subvector is positive. Under this conditioning, the subvector is again multivariate GP, but with an updated dependence object. The practical message is clear. When working with a subset of variables, either refit the model on that subset or carefully propagate the dependence structure from the original model. The last slide discusses stability under non-negative linear transformations. Suppose all margins share the same shape parameter and we apply a non-negative matrix to the vector. This covers aggregation and mixing operations, such as forming portfolio losses or regional risk indicators. The proposition states that after conditioning on the transform vector being in the L region, the result is again multivariate GP. The scale vector is transformed linearly, the common shape parameter is preserved, and the dependence object is updated. The practical implication is important. Under suitable conditions, multivariate GP models remain coherent under aggregation.